Hello all. In this lecture, we will discuss the distribution of primes that we have already discussed in the previous chapter. Here we will have a look at this distribution of primes again under the section the fundamental theorem of arithmetic. Actually, this is the last topic of the chapter greatest common divisors, chapter 3 of the prescribed textbook. So let's move to the lecture. In the second chapter, we have already discussed the division algorithm, isn't it? So by division algorithm, we know that if A is a positive number which is divided by B, A is divided by B, then there exists unique integers. Unique integers Q and R such that A is equal to BQ plus R with a condition on R such that R is always non-negative, 0 less than R and which is less than the divisor. Okay. So similarly, if we fix B is equal to, if we fix B is equal to 2, then uh, we can write any integer A as of the form 2Q plus R 2B plus R with the possible value of R is either 0 or 1. So since it is strictly less than B. Okay, that means any integer is of the form A is of the form 2B or 2Q, not B, it is Q. We take the quotient as 2Q. So any integer is of the form 2Q, 2Q or 2Q plus 1. And we have made the classification as either even or odd. So any integer can be either even or can be written as either even or odd. That means any integer is of the form whether belong to this category or belong to 2Q plus 1. And similarly, if we fix B is equal to 3, we can write any integer is of the form 3Q plus R with R having the values 0, 1 or 2. Isn't it? That means any integer is of the form either 3Q plus 1 or 3Q plus 2. So any integer belong to this category. And hence if we fix B is equal to 4, we know that any integer is of the form or every integer is of the form 4Q plus R, or we can write now it as 4N plus R, where R is equal to what are the possible values 0, 1, 2 and 3. So every odd integer, that means every integer either belongs to which categories, either is of the form, every integer is either of the form 4n or 4n plus 1, 4n plus 2 or 4n plus 3. So in this 4 types, every integer should lie either of these 4 types. Okay, so if n is equal to 4, if any integer is equal to 4 and it is even. And also we know this is also 4n plus 2 is also an even number. And any odd integer must be of the form 4n. Since 4n is even, 4n plus 1 will be odd. And we know if 4n is even, 4n plus 3 is also odd. So every odd integer is of the form if we consider any odd integer, it is of the form, we can write with 4 as the base or divisor, we can write any odd integer is either of the form 4n plus 1 or 4n plus 3. Okay, for example, if we consider 17, we can write it as 4 into 4, 16 plus 1, isn't it? 4 into 4 plus 1. So this is of the form 4n plus 1. Similarly, if we take 29 also we can write it as 4 into 7 plus 1. Again of the form 4n plus 1. Now if we consider 15, what about 15? 15 is 12 plus 3, that is 4 into 3 plus 12 plus 3. So this is of the form 4n plus 3, and similarly if we write 30, if we consider 35, 35 we can also write it as 32 plus 3. So 4 into 8 plus 3, again of the form 4n plus 3. Similarly, we can prove that we can see that any odd integer is either of the form 4n plus 1 or 4n plus 3. Okay. So when we consider, look at the positive integers of the form 4n plus 3. Now, look at the positive integers of the form 4n plus 3. Okay. The first 11 such numbers, the first 11 such numbers are when n equal to 0, the number will be it is 3, then 7, then 11, then it will be 15, 15 plus 4 it is 19, then 23, then 27, 31, 35 plus 4 39, again plus 4 43, of which so these are the first 11 numbers, odd numbers of the form 4n plus 3. Okay, of this you can see that 3, 7, 11, 19, 23, 31, 43, that is 1, 2, 3, 4, 5, 6, 7. Of these 7 are primes. Of these 7 are primes. That means from this we can make a conjecture that if we consider an integer of the form, that means so every odd integer of the form 4n plus 3. If we consider the first 11 numbers of the form, first odd numbers of the form 4n plus 3, we have seen that there are at least 64 percentage of these numbers. 7 means out of these 64 percentage are primes. That means from this we can make a conjecture that numbers of the form, or there are infinitude primes of the form 4n plus 3, isn't it? So our conjecture is, so there is made a conjecture. There are infinitely many primes of the form 4n plus 3. So this was our conjecture. So in order to prove, before proving or disproving this conjecture, we will need some groundwork result for this. That is given by a lemma. It is lemma 3.5. The statement is the product of any two, it's very clear result. The product of any two integers of the form 4n plus 1 is also of the same form. That means if there are two integers which are in the form 4n plus 1, then their product AB will also be in the of the form 4n plus 1 for some other integer n. Okay. So, proof is very simple. You can also try this one. So let A and B be any two integers of the form. We take let A and B any two integers of the form 4n plus 1. Okay, then 4n plus 1, that is specifically writing let A is equal to sum 4l plus 1 and let B is equal to sum 4m plus 1. Then their product AB is equal to 4l plus 1 into 4m plus 1, which is equal to 4 into 4, that is 16lm plus 4l plus 4m plus 1. So taking 4 outside, we can write it as 4lm plus l plus m plus 1. So which is equal to A of the form 4k plus 1, where k is an integer given by 4lm plus l plus m. So we have proved that the product of any two integers of the form 4n plus 1 is also of the same form. Now we move to our theorem. Or before moving, we can also say that this result can be extended finitely. That means any finite number of integers of the form. If there are finite number of integers of the form 4n plus 1, then their product also will also be in the same form. Okay. Now we are ready to prove our conjecture. It's the conjecture, actually it is true. We state this as theorem. Theorem 3.15. That is, there are infinitely many primes of the form four n plus 3. So proof is obviously by contradiction. That is, we assume that, or suppose on the contrary, proof by contradiction method. Suppose on the contrary that there are only finitely many primes. Suppose that there are only finitely many primes of the form 4n plus 3 of the form 4n plus 3. Let the primes be, say, p naught, p1, p2, etc., pk, which are in the order. That means in ascending order. That is where p naught the smallest prime, p naught of the form 4n plus 3, that is, let it p naught be 3. Okay, so pk is the largest prime of this form 4n plus 3. Now we consider the positive integer n. Consider the positive integer capital N is equal to 4 p naught p1 p2 etc. pk plus 3. And pk is the largest prime of the form 4n plus 3. Now it is clear that n is greater than pk, the largest prime, and is also of the same form, and is also of the same form, that is some 4k plus 3. It is of the same form. Okay. So there may be two cases arise. We don't know whether this number is a prime or composite. So if can n be a composite or prime number, we first check that case. So case 1, is it possible that n is a prime? If n itself is a prime, then what happens? Is it possible? If n itself is a prime, then in the last statement we have already stated that n is greater than pk. And what is pk? pk is the largest prime number possible in this order of the in this form 4n plus 3. So if n itself is a prime, then n would be a larger than n would be larger than the largest prime, that is pk of the form 4n plus 3. So this will make a contradiction. That means n must be a composite number. So we will consider case 2. Suppose n is composite. Suppose n is composite. Now what happens if n is a composite number? 4n plus 3. N is of the form 4n plus 3. That means n is an odd composite number. That is n is an odd composite number. And being a composite number, it has factors. It has divisors other than 1 and n. And being odd, each factor is either of the form 4n plus 1 or 4n plus 3. Since the only odd integers, every odd integers are of the form 4n plus 1 or 4n plus 3. So we can say that hence n is an odd composite number. Hence every factor of n is of the form 4n plus 1 or 4n plus 3, since odd into odd is only odd only. Now we will check whether each factor is of the form 4n plus 1 or 4n plus 3, or is there any mixed factor. So if we rule out the case if each factor is 4n plus 1, what will happen? If every factor is of the form 4n plus 1, is of the form 4n plus 1, we have just proved a lemma that saying that a product of any two integers of the form 4n plus 1 is also of the form 4n plus 1. So if every factor is of the form 4n plus 1, then n must be also of the form then n must be of the form 4n plus 1 by lemma 3.5. So that is if every factor is of the form 4n plus 1, then n must be of the form 4n plus 1 by the above lemma. But this is not possible, since we have already proved that we already know that n is of the form. But since n is of the form what 4n plus 3. So at least one of the prime factors must be of the form 4n plus 3. So n is of the form 4n plus 3. At least one of the prime factors prime factors of n, say we denote it as p. Say p must be of the form 4n plus 3. Okay, that is, or we can write it as p equal to 4n plus 3 is a factor of, is a prime factor of what, capital N. That is, n has a prime factor of the form 4n plus 3. And we know a smallest prime factor of the form prime of the form 4n plus 3 is p naught, that is p naught equal to 3, isn't it? So if we consider the cases whether is it possible that p can be 3 or not. Okay, so let p equal to 3, that is our p naught, p equal to p naught equal to 3. Then what happens? Uh, we know what is n. N is equal to 4 p naught p1 etc pk plus 3, isn't it? So p equal to 3 means p divides, or 3 divides what, this p naught is 3. Okay, so 3 divides this 4 into this product, and 3 divides 3 also. So 3 divides p naught and 3 divides 3 implies 3 divides what, n, isn't it? Or sorry, we can say not like this. We can say that 3 divides n and 3 divides 3. Then 3 divides n and 3 divides 3. Then by 3 divides its linear combination properties of divisibility, we can say that 3 divides n minus 3. Now what is n minus 3? This implies 3 divides n minus 3, that is 4 p naught p1 p2 etc pk. And we know if a p is a prime number which divides a1 a2 etc ak, then we have already proved, there is one proved result that p divides ai for some I, isn't it? So from this we can rewrite this as 3 divides, this means 3 divides 2 into 2 p naught p1 p2 etc pk. So this implies either 3 divides 2 or 3 divides pi, p divides 3 divides pi for 1 less than or equal to I less than or equal to k. Now we consider whether these cases are possible or not. 3 divides 2 is 3 does not divide 2. We know 3 and 2 are primes, and similarly 3 does not divide pi since each pi is a prime number. So this is impossible. But this is impossible. So p cannot be equal to 3. Okay, so p cannot be 3 equal to, that is p not equal to p naught. Now the second sub case is whether p equal to pi for 1 less than or equal to, sub case 2, let p equal to pi, p equal to pi for 1 less than or equal to I less than or equal to k. So p can be any of the primes 1 to k, isn't it? Since there is only a finite number of primes we have already assumed, and we obtained that 4n p is equal to 4n plus 3 is a prime factor of capital N. Then p must be of at least of the one of these pi's from 1 to k. Subcase 1, we have showed that p cannot be equal to p naught. So the only possibility is p is at least one of these k primes. Then if p is equal to pi, then we can say that p divides n. P divides n, that is, this is because we have written pi as a product of two factors in being a composite number. Of this, one is p. So p divides n we already know, and since p divides at least one of the pi, p divides the product for p1, p2, etc. pk. Uh, that is sorry, p for p naught, p1, etc. pk, since p is at least one of these p1 to pk. So again, by the properties of divisibility, we can write p divides n minus 4 p naught, p1, p2, etc. pk. And what is this? This is 3. This implies p is a prime number which divides 3, which is again a contradiction. So we have uh, uh, checked all the possible cases, and in all cases we have obtained a contradiction. And these both cases leads to therefore both cases lead us to a contradiction. So our assumption must be false. Our assumption is false or must be false. Thus, we have proved that there is infinite number of primes. There are infinite number of primes of the form 4n plus 3. So there are infinitely many primes of the form 4n plus 3. So naturally there may arise a question that whether there are infinitely many primes of the form 4n plus 1 or not. So the answer is yes, and you can verify this or prove this in the same way as an exercise. Okay, so actually these two results are special cases of some remarkable result which was proved by Dirichlet in 1837. But actually the problem or the conjecture was raised by Legendre in 1785, but proved by Dirichlet, and hence it is known as the Dirichlet theorem. Actually, the two cases we have already discussed are the sub cases or special cases of this remarkable result, and the proof of this theorem is somewhat complicated, and hence we here we state only the result. The statement is, if A and B are relatively primes, then the arithmetic sequence A, A plus B, A plus 2B, A plus 3B, etc. contains infinitely many primes. So this is the statement of the theorem. We already told that the two cases, that means there are infinitely many primes of the form 4n plus 3 and also of the form 4n plus 1 are the special cases of this theorem. Because when we take when a equal to 3 and b equal to, if we take 4, then the sequence becomes sequences what, first term a, that is 4, then 4 a plus b, 4 plus 3, that is 7, then a plus 2b, 2b means 8, 8 plus 3, that is 11, etc. Okay, so these are infinitely many, there are these, that means these numbers are of the form 4n plus 3. Okay, there are infinitely many primes. Now if we consider a as 1 and b equal to 4, it follows that infinitely there are infinite, it follows that there are infinitely many primes of the form 4n plus 1. Okay, hence the two cases are the special case of this Dirichlet theorem, which is a remarkable result in number theory. Okay, so let's wind up our lecture here. And the chapter, the greatest common divisor chapter is over. And in next class, we can take a new topic. Okay, thank you all.